In this video, we are going to discuss how to calculate electrostatic force on a charge in two dimension using superposition principle. Let's discuss question 1.48. Charge Q1 equals 1.40 times 10 to the power negative 8 coulomb is placed at the origin. Charges Q2 equals negative 1.80 times 10 to the power negative 8 coulomb and Q3 equals 2.10 times 10 to the power negative 8 coulomb are placed at points given by these coordinates. So Q2 is placed at 0.180 meter on the x-axis, whereas its y-coordinate is 0. That means charge Q2 lies on the x-axis at a distance of 0.18 meter. For Q3, on the other hand, its x-coordinate is 0, whereas the y-coordinate is 0.240 meter. So Q3 lies on the y-axis at a distance of 0.240 meter. We need to determine the net electrostatic force, both magnitude and direction, on charge Q3. Now, before we calculate the magnitude of the force, we need to first sketch the direction of forces acting on Q3. Now, Q3 is a positive charge, and Q1 is also a positive charge. So they will repel each other. So because of Q1, Q3 will be pushed up in this direction. So we can write the force acting on charge Q3 because of Q1 to be equal to F13, which is acting along the y-axis in the upward direction. Q2, on the other hand, is a negative charge. So it will attract Q3 towards itself. So force on charge Q3 because of Q2 will lie along the line joining them and point towards Q2. Because they are opposite charges and Q2 will pull Q3 towards itself. So we can write this force as F23. Now F13 lies along the y-axis, but F23 neither lies on the x-axis nor on the y-axis. And whenever you have a vector which doesn't lie on any one of the axes, we need to split that vector into its component form. So F23 we will split into its component. One component going along the x-axis, which we will call as F23x, and one component going along the y-axis, which we will write as F23y. So these are all the forces acting on charge Q3. Now we are going to find their magnitude. So let us start with calculating the magnitude of each of these forces. We will first begin with F13. I will write F13 as K Q1 Q3 over R13 squared. R13 is the distance between charge Q1 and Q3, which is 0.240 meter. Now let's substitute. K is 9 times 10 to the power 9. Q1 we write as 1.40 times 10 to the power negative 8 coulomb. Q3 is 2.10 times 10 to the power negative 8 coulomb over the distance between them 0.240 squared. And when you solve this, you get F13 to be equal to 4.59 times 10 to the power negative 5 Newton. Then we do the same thing for F23. F23 will be equal to K Q2 Q3 over R23 squared. So we substitute. K is 9 times 10 to the power 9. Q2 is negative 1.80, but we don't take that negative sign here. We just write it as 1.80 times 10 to the power negative 8. Q3 is 2.10 times 10 to the power negative 8. And R23 is the distance between charge 2 and 3, which is this line here. We can calculate this distance by using Pythagorean theorem. So I will write R23 to be equal to square root x component squared plus y component squared, which you can write as square root of 0.18 squared plus 0.240 squared. And when you solve this, you get the distance R23 as 0.3 meter. So let's substitute that here, 0.3 squared. And when you solve this, you get F23 to be equal to 3.78 times 10 to the power negative 5 Newton. Now, after I find F23, I need to find its x and y component. Let the x component of force F23 make an angle theta with it. And from the figure, I can write this angle also as theta as they form a pair of edges in angle. And we can calculate this theta by using trigonometric ratio. We have the opposite and the edges inside of theta, so we can use tan theta to find its value. We write theta equals tan inverse y component over the x component. So that will be tan inverse. Y component is 0.240. X component is 0.180. And when you solve for this, you get theta as 53.13 degree. I can use this value of theta to find the component of F23. So let us start with the x component. F23x can be written as F23 cosine theta. Substitute 3.78 times 10 to the power negative 5 cosine of the angle 53. When you solve this, you get x component to be equal to 2.27 times 10 to the power negative 5 Newton. Then we do the same thing to find the y component. We write F23y equals F23 sine theta. That is equal to 3.78 times 10 to the power negative 5 sine of the angle 53.13. And that gives you the y component to be equal to 3.02 times 10 to the power negative 5 Newton. Now, after we find these individual forces, we can find the x and y component of my resultant force by adding all the x forces together and all the y forces together. So let us find the net force acting along x-axis. This you get by taking a vector sum of all forces going along the x-axis. And if you notice from the figure, we have only one force along x-axis, which is F23x. And since this force is going to the right, we take it positive. Value of F23x we already found, which is 2.27 times 10 to the power negative 5 Newton. On the y-axis, we can write the net force as vector sum of these two forces. When you take the vector sum, we have to take the sign into consideration. Since F13 is going up, we will take it positive. F23y is pointing down, so you have to take it negative. So I can write the net force along y-axis as F13 minus F23y. Let's substitute F13 we found to be 4.59 times 10 to the power negative 5 minus F23y is 3.02 times 10 to the power negative 5 Newton. Solve this and you get the net force along y-axis to be equal to 1.57 times 10 to the power negative 5 Newton. Once I find the net force along x-axis and the net force along y-axis, we can find the magnitude of resultant using the Pythagorean theorem. We write the magnitude of resultant force F net to be equal to square root x component squared plus the y component squared. So let us solve this. X component is 2.27 times 10 to the power negative 5 squared plus y component is 1.57 times 10 to the power negative 5 squared. And after solving this, you will get the magnitude of the net force to be equal to 2.76 times 10 to the power negative 5 Newton. After we find the magnitude, we can find the direction of this force using theta equals tan inverse F net y over F net x. So let's substitute tan inverse of 1.57 times 10 to the power negative 5 over 2.27 times 10 to the power negative 5. And you get theta equals 34.66 degree. And this theta is from positive x-axis because both my x component and y component are positive. That means this resultant vector lies on the first quadrant. So this is how you calculate the net force, both magnitude and direction for forces acting on a charge in two dimension. You can divide this into steps if you want. The first step will be always to draw the direction of forces and split them into components wherever required. Second step will be to find magnitude of each of the forces. Third step will be to find components of forces which neither lie on the x-axis or the y-axis. And if the angle theta is not given to you, you can always calculate theta using any of the trigonometric ratios. Fourth step will be to find the resultant of force along x-axis and y-axis separately. Fifth step will be to find the magnitude of that resultant using Pythagorean theorem and then find the direction.